Hi everyone, here Andrea, and today we're gonna see how MATLAB app works for iPad. And of course, we have a little journey in the environment of MATLAB app and have a little example on control system. So, go directly to the MATLAB app. Here we have the environment of the command window. Inside that, we can just implement new variables, like for example, x equal to, and we implemented a variable named x, and it's equal to 2. So focus on the left-hand side. Here we have a legend. Inside we can find the name of the MathWorks account, it's me of course, and the files you opened previously, and of course the files of MATLAB drive. Here, for instance, we can find a folder of mine, and then command window to go directly to the command window you have seen previously, and then the sensors. Here, there are lots of sensors inside iPad, and you can collect lots of data from them. For instance, the acceleration, magnetic field, orientation, angular velocity, and position. So, for instance, if I want to collect acceleration data, like this one, you can just click on Start and then try to collect those data. As you can see here, the numbers are quite still. That means that the iPad is still, of course, on my table. But if I want to move it, you can just see how the numbers changes. But yes, now disable it and go on. Here we have some examples, like live scripts, when you can find how to use the lots of things you can find inside MATLAB app. And for example, for the plotting or for symbolic equation solving. So let's try to have a more precise look on files. Here you can open new files and create new ones, like new scripts or new live scripts. Yes, inside MATLAB, in MATLAB app, you can find live scripts. Okay? So, if you want to have a closer look on commands, yes, you can just implement new examples. Let's try to clear them. For instance, I would like to plot the sign. Okay, so introduce a symbolic variable like x. And then if I want to plot the sign, I just write as plot of x, of the sign of x. As you can see here, the plot is this one. If I want to collect more data, for instance, if I want to know if it's in 0 is equal to 0, just move the cursor and find that it's, yes, of course, is 0. But yes, move on. If I want to plot something more on the same plot, I need to write hold on, and then write as plot of, for instance, the cosine of x, and maybe I want to add the legend, writing sine of x and cosine of x. In the plot, as you can see, there is of course in red the cosine and in blue the sine. Yes, now move on. We can just clear here all the variables and of course the command window. So let's now have a look at the live script of today, iPad MLX. This is the environment where you can edit your live script and of course create whatever you want. In this example, we will see the control system toolbox and the application of some of its features. Okay, so let's study an input, for instance, like a step plus a sine wave. So introducing the symbolic variable t and study the input in the time domain. As you can see, here we have our input. So, if you want to change and go to the Laplace domain, you just write Laplace plus your input, and as a result, you will have the Laplace domain of your input. But if you want to study your input in a more precise way, then you need to introduce a new variable in a transfer function form. In this way, your input can be right in this way, and as a result, here the continuous time transfer function. But for instance, if you want to consider a more complex transfer function, you can see that there are lots of features, like this one, zeta pk. So if you have a transfer function really complex, like this one, you can just write a zeta pk and you will create a zero-pole gain model. In this way, you can find the poles and the zeros of your transfer function and understand the stability of your system. Moreover, you can just use another feature like R locus, which is really easy to understand if the transfer function is stable or unstable, just having a look on your diagram. In this way, TF you can really definitely understand that is unstable. Okay, so have a look. I have something else. For instance, the application of TF is really interesting. Just because we use it in a way, but here we use it in another way. In this way, TF is really useful to create a new transfer function in a smarty way. You just write in some numbers, you can just create a continuous time transfer function. And if you want to understand if it's stable or not, you can just write zeta pk of this transfer function. I will see that there is a pole in the origin at 2 poles in -1. If you want to study, moreover, the Bode diagram of this transfer function, you can just write Bode of that. As you can see, there are 2 plots, one for the magnitude and one for the phase. But moreover, Bode can be used in a different way. For instance, in this way, you can obtain the data for a precise frequency. For instance, for 1 radian per second, I can find that the magnitude is 0.5, not in decibel at all, of course, and the phase is -180. So, we arrived to the Bode criterion. The Bode criterion is really useful to understand if your plant is stable or not, and if it needs a control. And if it does, then you can create a controller. For the Bode criterion, you can use margin to plot the Bode diagram of your transfer function and understand the margins for the magnitude and the phase. For instance, in this case, F has a gain margin of 2, not in decibel of course, for 1 radian per second, and the phase margin is 21 degrees for 0.68 radian per second. Going on, you can just apply the Nyquist diagram to understand the stability of your plant, but of course this is another criteria. Going on, we have our application. Okay, so we arrived at our application. Let's now apply this function to design a PID controller on a plant called G. The desired properties of our controller are 0 steady-state error in step response, the crossing frequency at 10 radian per second, and a phase margin greater than 80 degrees. Let's now plot our G plant here on Bode diagram, and as a result we can see that the magnitude and the phase for 10 radian per second are 0.07 and -134. Since the natural margin of G is less than 80 degrees for 10 radians per second, we must implement a PID controller. Let's start with the PI to obtain a zero steady state error and to cancel a pole. Of course, this is for reducing the settling time. So I implemented it and I applied it on the plant. And as the Bode diagram shows, I don't change the magnitude and the phase. But of course, going to zero, I have implemented this zero error. Okay, so after that, I can see that the margin is not achieved. Thus, I created a new controller called RPD with a optimal phase and minimum gain. After that, I implemented it on the plant, and as a result, I can see from margin that the phase is actually minus 100. Thus, the margin for the phase is achieved, but not for the magnitude. Thus, I need to adjust the plant with a gain, and the gain is Kp, and the result for this is that the margin, of course, for the phase is not changed at all, but yes, for the magnitude. In fact, for 10 radians per second, we have the perfect phase and the magnitude exactly on the crossing frequency of 10 radians per second. We can have a look at our locus, and as you can see here, of course, the system is stable, and also for the Nyquist diagram, in which you can see that our system is quite far from -1. Okay, this has been our application. Hope that you enjoyed it. And if you need to contact us for anything, like from clarify something from this little video or everything else, you can just join our Facebook group and contact us directly there. So, hope that you enjoyed this and see you guys.